expert demonstrations for deformable object manipulation. And this is joint work with Alex Lee, Sandy Huang, Eric Tzeng, and Pieter Abbeel. So today we're going to be talking about deformable object manipulation, and the task we're going to be using as our example is an overhand knot tying task. So we're going to take the robot, we're going to put a rope out in front of it, and we're going to tell it a goal, which is to tie a knot. So this is a manipulation problem, and the first question you might ask is, well, can we solve this by planning? So can we use some sort of forward model of dynamics or something like that to solve it? And when we look at that, we're going to see that that's quite challenging. The first challenge we're going to run into is that the action space is a subset of R to the 14 because we've got two arms that are 7 degrees of freedom. So that might be tough. The horizon's 100 or so, if you're considering individual arm motions of some size. And our state space is really where things really blow up. And the reason this number is so large is because if we think about representing the state of a rope, right? So our rope's in simulation here, and we represent it with 72 points along the rope. And so those are 72 points in R3, and representing and planning over a space involving that is beyond current methods and likely going to be challenging for quite a while. So planning's not directly an option in this problem for us. So we're going to take a different approach, which is going to be use expert demonstrations in order to figure out what trajectories to do. And in particular, we're going to be talking about doing trajectory transfer from demonstrations. So trajectory transfer is the idea that I show a robot an example trajectory of performing a manipulation, and we're going to ask it to modify that trajectory appropriately to fit a new scenario. So the way that we approach trajectory transfer is we consider representing our scenes with sets of points, and we say this is our train situation, and then we demonstrate some trajectory in that. And now we get a new situation, and the question is, what do we do here? So our approach to this is we consider that there's some function that maps between one space of our problem to another, and we're only going to consider the end effector trajectories to make things a little simpler. So we'll consider these points to be samples of some function f that goes from R3 to R3, and then we can find correspondences between them, fit a function, and pass our end effector trajectory through that. And we get an example of a trajectory here that looks like it does roughly the same thing and is analogous to the previous one in some way. So what does this actually mean? Let's be a little bit more concrete about it. We have our demonstration, which we represent as a set of points in our scene, and our trajectory, which is a set of poses. We have a test scene, which is a different set of points. So the first thing we do is we pass it into a process that's going to find correspondences between the points and fit a transfer function, output some f star, which we're going to use. Then you pass that into some transformation technique, which is able to transform the poses from the initial trajectory. And we get out a new set of poses. And then last, that new set of poses, there's no guarantee that that trajectory is actually feasible. So we pass it through a round of motion planning to find a trajectory that's nearby, but is feasible for the robot to execute. Then we ship that off to the robot and execute it and hopefully succeed in tying a knot. So this is an example of our setup running on the PR2. This is us recording a demonstration here. You can see we're just going to guide it through. So what's happening in between each of the actual trajectory steps is we're taking a picture with the Kinect and we're recording the point cloud that we actually get there. So see there, it's the end of the demonstration. And now we're going to give it a new rope. Notice this is different. And you can see up in the top right here what we're doing is we're registering the points together, and then we're fitting a function to map between the two spaces. And the particular functions that we use for this are thin plate splines, which are functions that minimize the rigidity, maximize the rigidity in the mapping. And that's motivated by the fact that a lot of manipulations are going to succeed in transfer under rigid transformations. And then I'll just let it finish this last step here, and you can see that we successfully managed to tie the knot. So here's a list of references if you're interested in reading up more on this particular technique. Great, so this is a technique that'll let us transfer if we've got one demonstration for doing a particular step of the task. Right, so that works all well and good, but what happens when we have this scenario here? We get a bunch of demonstrations for maybe different ways of performing the same task, right? We'd like to be able to leverage that information and improve performance if we can have multiple demonstrations. Maybe one demonstrates how to tie a rope with your right hand, one just demonstrates how to tie with your left, and they have different properties to succeed in different kinds of ways. So the approach we take here is you could imagine something like averaging. You could try to learn how actually the structure of that manipulation there. The approach we're going to take is just say, well, let's just pick the best demonstration. Let's find one that's going to maximize the chance we succeed the task, and then if we cover our space well enough with demonstrations, we'll do quite well with that setup. And the question that I'm going to be talking in depth about and that this work centers on is how do you solve that question? Like, how do you actually pick that? So there are some considerations we want to take into account. The first is that different demonstrations obviously will lead to different next states, right? So from that perspective, we want to be careful of picking them. And in particular, as you saw when I was trying to untangle this up here, there are frequent dead ends. There are states in the state space where our robot just has no idea what to do anymore, just throws up his hands and gives up because the rope's gotten entangled or it's been knocked on the floor or something of that nature. And then you may want to trade off some objectives, so maybe success rate versus execution time. And so there's been some previous work looking at this problem from ISR 2013, and it said, well, we decided that rigidity is a good thing, so just select the most rigid one. And that's a reasonable idea to do, but how can we improve on this? Can we do better? And the answer is we can. But in order to get to that point, the first thing we want to do is we want to look at what's actually happening when we transfer a trajectory. What's actually going on in that process? So here what I've done is I've just put up the section of that trajectory transfer diagram that just transfers the trajectories. And what's interesting is you can take this pipeline. Oh, and the other thing I've done is I've actually built the demonstration into it. So this is a single demonstration that you could imagine hard coding into the procedure. And now, if you look at this on its own as sort of a system for computing things, what does it do? It takes in new scenes and it gives you trajectories. So this is something like a policy for picking trajectories. So it's a policy where you combine a transfer method with a particular demonstration. So you can simplify our diagram. Now it looks like that. It's a little bit simpler, a little bit easier. And it's picking trajectories, which are not necessarily in our action space, right? So what happens then is you feed this into a trajectory controller, which will actually follow the trajectories and move them around. So this is best described as a policy for picking an option. So options are the way that you extend MDPs to have temporal abstraction. And what they are is they're a combination of a policy with a termination condition. So for a trajectory, that policy is just moved through each of the waypoints, and then the termination condition is that you reach the final waypoint. And then selecting an option in an options MDP simply runs that option until you hit the termination condition, and then stops and returns control. So now, what we can say is that we've got our original MDP, which is intractable, we don't know what to do. Now we get a demonstration library, and what happens? We get an options MDP, which is parameterized by our demonstrations. And we can look at this MDP and ask, is this easier? Does it seem like it's something that we can actually deal with as opposed to the original problem? And so we've got here is the original MDP on the right. And now if we look at the action space, well, we've gone from R14 to 150, if you have 150 demonstrations. And the important thing is that it's a finite set. It's something you can actually deal with and consider. Our horizon has gone from on the order of about 100 to on the order of about 4. Right? It takes, you saw from that rope demonstration, that was just 3 steps to tie a knot rather than having to plan through each of the individual waypoints. And then the state space is still the same. So we still have that issue, we need to overcome it. But we can recognize that the rule that we had for selecting things earlier was just a policy in this MDP. And we can try to learn a policy there to maybe do better or improve on it. So that's the way we're going to go about going forward. And the approach that we took to that is a max margin approach. So we featureize the combinations of a state and a demonstration and maybe some properties of the trajectory transfer. And then we have as humans just say, okay, in this state, transfer this demonstration. In this state, transfer that demonstration. And then we can compute what are the other opportunities you could have had, find a maximum margin separator. So this corresponds to this optimization where this says maximize the margin, and this says prefer the expert selections. And we gather demonstrations by just watching simulations of the robot execute, picking the best one from our heuristic guesses. Use a structured margin so that you can have demonstrations that are similar, because it turns out that a lot of them would have done essentially the same thing in the same state. And then you need slack variables to cope with suboptimality in your choices. So now we've got a way for learning policies, and we can test that out. So to test that out, we looked at some simulated robot tasks. And to generate a distribution over initial states, we took the initial states from our rope distribution and looked at perturbing them in different ways. So in particular, you pick 7 locations, and you can perturb those by a random amount, up to 10 centimeters. And here are some samples from our distribution centered around this state. So you can see we actually do get fairly different states. And then this is what it looks like if you go ahead and execute that. So it's going to run the correspondence, do the motion planning, and then this is our simulated environment. It's using bullet physics to model the rope. So how do we do when we do that? Well, if you just take this policy, get 72% success rate on 100, on a hold outside of 100 knots versus 56 before. So that's great. But we'd like to see, can we do better? right? So you could look at feature design. But one of the things that you can notice from this, like things that we might want out of our objective function, our ranking function, is we might want to be able to make comparisons between states, right? We might want to have an algorithm that says, okay, well, maybe I need to trade off between transferring demonstration 1 in state 1 and transferring demonstration 2 in state 2. This optimization, the function we get out of this optimization doesn't really give us any good basis to do that. Similarly, we'd like to incorporate progress towards maybe, right? Our tasks are to tie a knot. This has no information about that other than the indirect information from the examples. And then maybe it'd be nice to have a natural interpretation. So the thing that we've ignored here is that we actually have an MDP. We know what the cost function is. In particular, we know what characterizes the optimal value function. And if you look at these criteria, what a function that meets it is the Q function, right? So what we can do is we just take that and add it into our optimization. And here we've just added in a line saying that the Bellman constraints from our demonstrations hold, and then we're just saying minimize the error on that. So now you can take that, rerun the same algorithm, learn, and then try out on the same holdout set, and you get a bump, up to 80% success rate. And what's cool here is that we're learning policies for complex manipulations. These are policies at a more abstract level than just learning sort of individual trajectories or things like that. And then now, so I mentioned we'd like to be able to compare between states. So the reason we'd like to be able to compare between states is because it was intractable to originally plan in our unabstracted MDP. But now we have the demonstrations, we have an option MDP. We can try search and see if a direct planning approach there will work out. And in particular, the horizon's a lot shorter, so that might work out for us. So what we're going to do is we're going to use physics simulation to expand our nodes. And the issue here is that this is pretty slow. So you're only going to get on the order of tens of expansions as opposed to thousands. But our horizon's short, so maybe we can still get something. We're going to use our learned Q function as a heuristic. It's comparable across states, so that's all good to go. And then finally, the branching factor is still pretty large. So we're going to use beam search to cope with that. And then if you take this and run this controller, you end up with a 94% success rate on that task. So, and then this is close to the best you could hope to do on this data set because our distribution over states actually has a reasonable number of states that are insolvable with the current set of robot demonstrations that we have. And so, yeah, and that sums up the main content portion of my talk. And just the next directions we're interested in taking this. Turns out that tying overhand knots didn't prove to be, or maybe solved it for this distribution. And we'd like to look at more complex tasks. I think really getting into longer horizon tasks is really important for us because right now, I mean, with the overhand knot, within 5 steps, if you can search out that far, you can solve most tasks. And what you really want to check is what happens when that's not possible. Are you actually learning a really good Q function? We think other robots might be able to work with this. So there's not very much specificity about how you actually transfer the end effectors of the robot or how you interact with the objects. And so we'd like to extend this to either maybe humanoid robots with motion capture or more complicated end effectors, so maybe human hands, where you transfer where the fingers go as opposed to where the finger pads of a robot are. And then finally, if we think about what's going on here, right? Trajectories are policies, and they're very particular types of policies that we know how to transfer with a function that just maps from R3 to R3. It's very clear. You've got a series of point attractors, you just transfer the point attractors through, and then you can just run the same controllers on it. But what if you have more general linear feedback controllers for your state? Maybe that would be an interesting thing to look at. Could you figure out a way to transfer that? Or arbitrary policies in an MDP. And so we'd like to experiment with that and see where we could go. That concludes my talk. Thank you for your attention. You definitely could. And I think going forward, we're also interested in looking at sort of direct reinforcement learning approaches in this space. The reason we picked this was mainly just because we wanted to get off the ground and get running, and this seemed, there's still a pretty large branching factor to the task. There are lots of unrecoverable states. It makes it hard to directly do reinforcement learning there. But yeah, we'd love to explore that. Yes?
Before you decided to pursue not tying, were you considering other tasks, and then not maybe talking to the one that worked? Or was it just, oh, let's do not tying?
Well, I think we started this with knot tying in mind. The main reason that we already had a pretty good set of demonstrations to work with knot tying. I'm going to try extending it towards other, either knot tying things, or different kind of, like folding is definitely an interesting application we're interested in. And you can also look at deformable tasks where the deformability is not in one object, maybe across a class of objects. So demonstrations that involve picking up this water bottle, and then how does that tell you how to pick up or manipulate an Nalgene or something like that.